Today, we're diving into object-oriented programming, or OOP, a fundamental paradigm in modern software development. This powerful approach helps us structure our code efficiently using concepts like classes and objects. Let's begin by understanding the core building blocks of OOP, classes and objects. Think of them as blueprints, and the actual things created from those blueprints, respectively. First, what exactly is a class in the context of object-oriented programming? A class serves as a fundamental blueprint, providing a template for creating specific objects. It defines the attributes, which are data, and methods, which are behaviors, that all objects of that class will possess. Essentially, classes clearly describe both the structure and the capabilities of the objects derived from them. Now, let's explore the concept of an object within object-oriented programming. Simply put, an object is a concrete instance that is created from a class. Each object is a unique, concrete entity brought into existence directly from its class blueprint. Objects maintain their own unique state through attribute values and can perform actions by calling their methods. To make this clearer, let's walk through a practical example using a dog class. We'll see how a class blueprint can be used to create a living object. Here, we define our dog class, specifying its shared characteristics and behaviors. The dog class defines a shared species attribute and an init method for unique name and age. The description method specifies a behavior. This code defines the dog class with a species attribute, an initializer for name and age, and a description method. Now, let's see how to create an object from this dog class and interact with it. Here, my dog is created from the dog class with a specific name and age, accessing its attributes and methods using dot notation. This code creates a dog object named Buddy at age 3, then prints its name and calls its description method. Next, we'll explore different types of inheritance, a powerful concept in object-oriented programming. Inheritance allows us to extend functionality and efficiently reuse code across related classes. First, we have single inheritance, a straightforward and common type. In this type, a subclass directly inherits properties and behaviors from just one superclass. Then there's multiple inheritance, which offers more complex relationships. Here, a subclass can inherit from two or more superclasses, combining their functionalities. Multi-level inheritance introduces a chain-like structure between classes. It occurs when a subclass inherits from another subclass, forming a clear inheritance chain. Hierarchical inheritance allows multiple specialized classes to stem from a single base. With this type, several subclasses inherit from just one single superclass. Finally, hybrid inheritance combines various inheritance types for complex designs. This involves combining two or more of the inheritance types we've discussed. Let's explore flexible object interactions, a key aspect of object-oriented programming that allows for dynamic behavior. This means objects can adapt their behavior by adhering to common interfaces, making our code more versatile and extensible. First, we'll look at method overriding, a powerful concept that allows subclasses to provide specific implementations for methods. Here, a subclass, dog, defines a speak method with the same name as its superclass, animal, providing its own specific behavior. This code demonstrates how the dog class overrides the speak method from the animal class, resulting in dog barks when called. Next, let's see polymorphism in action, which truly highlights the power of flexible object interactions. The animal sound function can work with different objects like bird and dog, as long as they both have a speak method. This code shows animal sound calling the speak method on both bird and dog objects, each responding uniquely. Now, let's delve into the pillars of encapsulation, a fundamental principle in object-oriented programming. Encapsulation is all about bundling data and methods together, while strictly controlling access to that data. It combines an object's attributes and its associated methods into a single, cohesive unit, which we call a class. This means we group related data and the operations that act on that data together within a class. Information hiding is crucial. It protects the internal state of an object from direct, unauthorized external modification. By doing so, we prevent other parts of the program from directly manipulating an object's private data. Attributes prefixed with a double underscore, like attribute, are designated as private, intended for internal class use only. These double underscore prefixed attributes signal that they should not be accessed directly from outside the class. Public methods, on the other hand, form the public interface, providing controlled access to modify or retrieve private data. These methods act as gatekeepers, ensuring data is handled correctly and consistently. Ultimately, encapsulation ensures data integrity, meaning an object's data remains consistent and valid through controlled interactions. This principle helps maintain the reliability and correctness of your object's internal state. Let's explore how to achieve abstraction using abstract classes, a powerful concept for defining common structures. Abstract classes essentially define a contract, outlining what subclasses must implement without providing full details. To define an abstract class, you use the ABC module and the abstract method decorator, making it impossible to directly instantiate. You declare abstract methods within these classes, specifying what methods exist but without providing any implementation. Next, you create concrete subclasses that inherit from this abstract class, agreeing to fulfill its contract. It's mandatory for these subclasses to provide complete implementations for all the abstract methods they inherit. Finally, only these fully implemented, concrete subclasses can be instantiated, giving them specific, executable functionality. Let's discuss customizing object behavior, a flexible way to make your Python objects interact uniquely. This begins with how your objects interact, for example, when you perform an addition or a string conversion. When these interactions occur, Python implicitly invokes special methods behind the scenes. These are known as magic methods or dunder methods, like _add for addition or _str for string representation. By defining these magic methods in your class, your custom logic then executes when Python invokes them. This allows you to precisely define how your objects behave for common operations, making them more intuitive. Let's now summarize the core object-oriented programming, or OOP, concepts we've explored throughout this session. These are the key takeaways you should remember to truly grasp and apply object-oriented principles effectively in your code. Remember, classes act as blueprints, defining structure, while objects are their concrete instances, holding both data and associated methods. Inheritance is crucial, enabling new classes to efficiently reuse and extend functionality from existing parent classes, promoting code reusability. Polymorphism allows objects from various classes to be treated uniformly via a common interface, enhancing flexibility and extensibility in your designs. Encapsulation bundles data with the methods that operate on it, protecting the internal state by providing controlled access to its components. Abstraction hides intricate implementation details, exposing only the essential features through abstract classes and methods for simplicity. Finally, magic methods and operator overloading customize object behavior for built-in operations, making your objects more intuitive to use.